All right, let's continue. So our next speaker is Professor Atsuo Kuniba from University of Tokyo, and he'll talk about a strange 5-vertex model and multi-species ASEP on a ring.
Thank you. Can you hear me? So I thank the organizers for very generous invitation. So first, I have to tell two things. So at this time of year, I occasionally experience mild allergy symptom, which may cause me to cough from time to time. So I apologize in advance that if it's disruptive, then thank for your patience and understanding. And the second thing is, so this was originally planned title, but what I'm going to talk actually is just a prologue to it. So because I think it's more suitable for this workshop or conference. So here is content of my talk. So I explain what's ASEP and stationary states, and so on. So this talk is a survey of the combinatorial aspects of the simple exclusion or zero-range processes that become intriguing in multi-species setting. So it is based on joint works with many people, but I found that the talk will primarily focus on the ASEP case, and in the latest preprint by the Oria Mandestram, who is the next speaker, and Travis Scrimshaw presents further developments. So let me fix my convention for n-ASEP. So we consider the periodic lattice of length L, with each side I is populated with a variable taking from 0 to n. So n is greater than or equal to 1. And it obeys the stochastic dynamics represented by this for this constraint. So it's a continuous time Markov process governed by the master equation of this form, where P is a probability vector. So sigma represents a configuration, and P is a probability for that this configuration is taken. And H is a Markov matrix, which is the sum of the local terms, nearest neighbor acting on the nearest neighbor sites by this rule. So now let me explain the stationary states. So this Markov matrix is split into the irreducible sectors. So this irreducible subspace, which I call the sectors, is labeled by this multiplicity arrays, like this. And each sector has a unique stationary state, which is annihilated by the Markov matrix. And that's I denote by P bar. And in this talk, I normalize the probability to the positive integer. So it is known that this vector is trivial for n is 1, which is a single species cases, in the sense that all the possible states are realized with an equal probability. But when n gets greater than 1, it becomes less trivial. So what is known about stationary probability, P sigma appearing here? This is a stationary state. So 2007, Ferrari and Martin invented a combinatorial algorithm to construct this quantity. And at around the same time, many people try to obtain the kind of explicit formula for this number by using the so-called matrix product approach. So my talk is a kind of somewhat approach from somewhat different angle. So in this setting, so in our approach, the Ferrari-Martin algorithm becomes a composition of combinatorial R. And matrix product operator is a corner transfer matrix of the Q equals 0 boson-weighted 5-vertex model. And this stationary probability acquires interpretation that it is a partition function of a 3D model associated with the tetrahedron equation. So I'm going to explain these things. So let me recall the Ferrari-Martin algorithm. So we are given the sector with labeled by the multiplicity array, and we consider this set, which is a set of states of the n-line Q, so a multi-line Q in general. So this symbol, which is a tensor product, is actually just product of sets, finite sets. And BS is a finite set. It's a set of 0-1 array of length L satisfying this condition. So for example, length L3 length 3 chain, we have this finite set. So element of BS or BS itself will be called a crystal from some context. And I introduced this number, which obeys this inequality due to this assumption. So this multi-line Q or n-line Q is elements. The elements are depicted as dot patterns. So for example, if n is 3 and length 7 chain with this sector, then it's depicted in this manner, where obviously you see that B1 is 0, 0, 1, 0, 1, 0, 0, as this example indicates. So the Ferrari and Martin gave a combinatorial construction of the surjective map going from the multi-line Q state to the state of the TASEP, such that the Puré image, number of a Puré image of this map agrees with the integer normalized stationary probability. So namely, the uniform measure on multi-line Q induces the n-TASEP stationary measure via this Ferrari-Martin map pi. So how it goes? So let me illustrate it in terms of examples. So let's consider n3 case. So this is a 3-line dot pattern. And the image is like this. This is a 3 TASEP configuration. How can one go from here to here? So starting from the bottom arrow, you connect it, or you pair it to some dot upstairs. And you continue this pairing until you reach the top row. And since these two captured dots are coming from the level 3 basement, so we assign the number 3 here. Similarly, we repeat this procedure for the remaining dots in the second row, and the captured dots are labeled as 2. And this one from the beginning here is just 1, and the remaining places 0. And this agrees the ASEP state. So the pairing of dots in adjacent rows is referred as a queuing process of customers and service. So the rule is as follows. So how to find the partner of the connection, the pairing? So you start from any dot, and its partner is the closest one to it's just above or to the right. So here, like this. And once you do this, then you proceed to the another unconnected dot and do the same thing. And to the right, I said, but it's to the right in the cyclic sense. So the precise connecting pattern may depend on which the order of the dots you pick up, but the final result is known to be independent of such choice. That's a Ferrari-Martin map. So from our point of view, this pi is most naturally formulated by combinatorial R of the quantum affine algebra, UQSL L hat. So remember that L was a system size, but this appears as a rank of the relevant quantum affine algebra, which is somewhat intriguing. So I finished chapter 1. And let's move on to this quantum group story. So I will explain what the quantum R first, and so on. So what is the quantum R matrix for this algebra? Well, there are many, well, actually infinitely many, but I focus on some specific R matrix relevant to our problem. So I consider the degree S antisymmetric tensor representation, BS, whose bases are labeled by this set BS, crystal BS, that I already introduced. So this BS is in one-to-one correspondence with the length S column-shaped standard tableau in obvious manner. And the quantum R matrix is a linear operator which intertwines or exchanges the order of the tensor product in this manner. So its action can be described in this manner. So I and J are taken from these length L01 arrays. and basis vector labeled by I and J are written in terms of the ket symbol. And this RGABIJ is a matrix element of the quantum R matrix. And it depends on the spectral parameter Z, as well as quantum parameter Q. So there exists a normalization such that this matrix element simultaneously becomes a polynomials in Q and Z. So here is such normalization for UQSLs we have and R12. All the other elements are 0. So quantum R matrix, you can derive such formula by many means. For example, in principle, you can take the image of the universal R by this representation. Or more kind of pedestrian way, you can determine the commutant of the action of the UQ, this algebra. So that gives you this result up to normalization, up to the choice of the gauge, so on. But there is a very useful, practically useful and efficient formula is known like this, which is a matrix product formula for the quantum R. This is less known, but very efficient. So this law is just a normalization to achieve the normalization that I mentioned. So, but it is explicitly known, but it's not necessary, so I omit. So this H and these L's, they are operators acting on the Fock space, whose bases are labeled by non-negative integer m. So this is infinite dimensional. And H is just a number operator. L has 4 indices taking value 0 or 1, since these arrays A and B, I, J are the length L array of 0 or 1. So I define this in detail in the next page, but in this page, I just give you the graphical representation, one interpretation. So I assign black arrow for these indices, A, B, I, J. So I going to A and J going to B. But as I said, this operator, L itself is an operator acting on the Fock space. So it's natural to introduce one more arrow, which is written in blue, perpendicular to this vertex. So if L is this unit constituent of the cubic lattice, then this product is naturally represented as a concatenation of this diagram along the direction of the blue arrow. And finally, you need to attach operator here.
I have a question about your blue line, the Fock space. Is it a bosonic Fock space?
Yeah, bosonic Fock space.
Okay, and the other ones are just fermionic, they are 0, 1?
Pardon?
The black lines are just 0, 1?
0 or
so
1, two-dimensional. So this is C2, and F.
F, okay, thank you.
Yeah. So this is barbecue stick with X-shaped sausages, according to Sergei Seliger, from whom I learned this diagram representation. But actually, this barbecue stick is winding, representing this trace. So this trace is taken over F. So it's an infinite sum. So now I have to describe the concrete form of this operator, depending on A, B, I, J. That's here. So I would call it as a 3D L operator or Q-boson weighted 6-vertex model. So as I said, ABIJ. So ABIJ defines this part, C2 tensor C2, like these arrows. But these guys itself are the operators acting on F. So its Boltzmann weights are the operators acting on F. What sort of operator? They are the Q-boson operators. So A plus acts on this manner, creation, A minus like this, annihilation, and K is a diagonal. So this last vertex I put in red. So later we will specialize Q to 0. So in this case, this drops out and we go to the 5-vertex model. So this Q-boson weighted Taylor operator appears in various contexts and guises. For example, it appears in the quantization of Michel's. Michel's theorem by Bajanov-Mangazev-Sergeyev. And also in the formulation of quantum groups by Okado, Sergeyev, and myself. And also quantum cluster algebra approach to the tetrahedron equation by Inoue-san and Terashima-san, Miyagi-san. Anyway, so I've explained the quantum R matrix, and I should go to the Q0 situation. So that's called combinatorial R. So remember that quantum R matrix is a linear operator depending on Q and Z acting in this manner. And here I picked up one example here. So if you specialize Q to 0, so exactly one term with coefficient 1 remains in the right-hand side, is red. So the combinatorial R is practically just a Q0 limit of the quantum R matrix in some good normalization gauge or base. And in this talk, I specialize Z also to 1 in this setting. So above example correspond to this situation. So 001, tensor 110 is get mapped to this. So namely that we lose all the linear superposition and we are left with combinatorics. So actually, according from the general theory of crystal base by Kashiwara, it is known that such limit, combinatorial R, becomes a bijection from this set to this set. And Yang-Baxter equation survives in this limit non-trivially. You see that in this example, it's not just a swap of the component, but something non-trivial is happening here. So this limit, one can retain some non-trivial structure, but you can go too smoothly to the combinatorics. That's what crystal-based theory does. So now let's depict this relation in terms of, again, this vertex diagram. But remember that this I, J, A, B are L array of 0 and 1, because the labeling set of this space is length L array of 0 or 1. So in that sense, I'm using a bold letters here and rather thick vertex here. Now here is an example of the Yang-Baxter equation. So given this element of the crystal, so this is actually thick arrow, but yeah, you apply combinatorial arrow here, here, and here, or here, 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 in a different order, but still the output is the same, although the intermediate states are somewhat different. So the combinatorial R is a decent or systematic, a decent systematic example of the set theoretical solution to the Yang-Baxter equation. From my point of view, it's the largest supply of this set theoretical solution to the Yang-Baxter equation. So this map or image can be in principle determined by taking a Q0 limit of the quantum R matrix, but there is a very combinatorial and efficient rule, which I'm going to explain in the next page. So how to find the image given I and J? And that is known as the Nakayashiki-Yamada rule. So let me illustrate it in terms of examples. So let's take this element I and J from B4 tensor B6. And we have to find something here. The rule is as follows. So we make it into the dot patterns here. So this I is 1, 1, 0, 0, 1, and so on. So dot, dot, nothing, nothing, 1, dot, and so on. And then you do this pairing. So you connect the dots, the closest dots, to the above or right cyclically, and so on. And once this pairing is completed, then there are remaining dots here. So you slide them down to get NP. So I shifted these dots downstairs and getting this one. So A is 0, 0, 0, 0, 1, 0, 1. So that's known as the Nakayashiki-Yamada rule. But as you see that this is nothing but the Ferrari-Martin algorithm I've already explained. So that the algorithm, in a sense, was known prior to their introduction by Nakayashiki-Yamada in the last century. And this is a story about a two-line process where we have two rows. What happens if we have more rows, n-line process where n greater than 2? That's even more intriguing. So again, let's explain in terms of an example. So here I consider the three-line dot pattern, the example we already used. And we know that this is the image. And these rows represent the crystal elements, 0, 0, 1, 0, 1, 0, 0, and so on. Now, I let these crystal elements interact in this manner. So these vertices denote the combinatorial R. So by the definition, so B3 is just this, since B3 is written here, 0, 1, 1, 0, 1, 1. But starting from given B1, B2, B3, after these interaction by combinatorial, things becomes non-trivial, but determined uniquely. And for example, in the first step, B2 becomes here, B1 becomes here. And now here is a quiz for you. What's the relation of these purple 0, 1 arrays and image of the Ferrari multi-map? So this is a quiz for 5 seconds. You see, it's very easy quiz. Yes, you got it. So this TASEP, local TASEP states nothing but height of the sequence 1 filled from the bottom. Namely, the southeast wedge of the corner transfer matrix. I would call it as a corner transfer matrix, see, according to the Rodney-Baxter. The southeast edge of the corner transfer matrix is the decomposition of TASEP state sigma by indicator functions. What is indicator function? This is an indicator that local states are greater than 2. This is an indicator that local states are greater than 1. This is an indicator function that local states are greater than 0. You can go from the TASEP states to the set of indicator function and back. It's bijective to correspondence. So through these observations, you can reformulate the Ferrari Multiplication result as a corner transfer matrix. So we should find an integer normalized stationary probability given configuration sigma, and it's a statistical sum over the crystal or the multi-line Qs. And this configuration or Boltzmann weight is 1 or 0. It is 1 if it matches this boundary condition specified by indicator function decomposition of the given TASEP state sigma. Otherwise, 0. So this is an n equals 3 case, and the result of the Ferrari margin and our findings that their algorithm is nothing but a IISc model. But now we know that this vertex is a combinatorial R, but combinatorial R is a Q0 limit of the quantum R, and quantum R had the barbecue stick formula. So we are to substitute that barbecue stick here, perpendicular to this screen. So what happens? So to be each vertex here, which is nothing but a combinatorial R, we are to substitute the barbecue stick formula at Q equals 0. So this thick arrow, actually this arrow is thick. It is resolved into the layers, the L layers, like this, in terms of 3D L operator at Q equals 0. So the Q boson weighted 6 vertex model at Q equals 0 becomes crystalline 5 vertex model where we lose the last vertex, but still it's non-trivial. It's very simple, but it's still non-trivial. So each layer forms the configuration of the crystalline 5 vertex model. So let me show the example again. So for example, n equals 3 case, its stationary probability becomes the trace of these operators, and x0, x1, x2, x3 becomes like this, where these 0 and 1 specify the boundary condition. For example, x0, you are not allowed to touch that southeast boundary, so only these configurations are allowed. And depending on these configurations, you substitute this rule. And since we have 3 vertices, that means it's the operator acting on the tensor cube of box space F. And I employ some specific ordering of the tensor product. Probably this is the first component, A1 plus here, and this is the second component here, and so on. Anyway, so by such reasoning, one can prove that the following theorem. So for general n TASEP, integer normalized stationary probability is a trace of the matrix product operators X, which is nothing but a corner transfer matrix of the Q0 boson valued or weighted 5-vertex model. So there are this number of vertices here. And these arrows are now thin arrow, just 0 or 1. And the choice R1 and 0 here correspond to the boundary condition to the specified by the indicator function. So this XR is a layer transfer matrix with triangular shape. It's a corner transfer matrix, but it's a layer transfer matrix. So layer because they are the operators acting perpendicular to the screen according to this Q0 boson. So this P sigma acquires interpretation of the partition function of the 3D system with prism shape. But this prism is again to be closed since we are taking a trace. Now let me remind you that we are in an interesting situation, intriguing situation. We started from the initial setup where we have length L periodic chain link, where each side is populated with such degrees of freedom. So the usual treatment of such system is length L chain of SN hat system, something like that. But now we are in a cross channel in the sense that the normal of the rank and size is interchanged. So this is a linear size N system, and apparently symmetry algebra has become SL hat at Q equals 0, as I mentioned. So such duality of size and rank has been observed in a couple of places in such problem in quantum integral systems. So anyway, let me repeat the status so far. So this is the corollary of the Ferrari-Martin theorem, or reformulation of Ferrari-Martin result, combined with the identification of their algorithm with Inoue law. So now I move on to the third topic. So, yeah.
Maybe I missed a point. What do you mean with on the xi, your graphical representation of xi as a corner transfer matrix? What does it mean? The 1 and the 0s you put on the diagonal? These are projectors, or
which one?
When you have this representation of xi as a sum over your corner transfer matrix.
Yes.
Yes, you say that you put I entries equal to 1 on the diagonal and that's 0.
Yeah.
And I was wondering, I'm not sure what it means. It means that you project.
Yeah, it's not project, but boundary condition.
Boundary.
So this is a configuration sum. And each edge takes 0 or 1. And every time you decide 0 or 1, you apply this, assign this Boltzmann weight, which is an operator acting on the Fock space. So it's a partition function of the triangle, vertex model triangle with 5 vertex model triangle. But Boltzmann weights are operators.
Okay.
Like this. Okay. Okay. So we have already seen a lot of kind of 3-dimensional things, and I would like to move on to that aspect. So that's chapter 3. So now let me recall the local form of the stationarity. So we had the operators with index runs from 0 and n. I symbolically write it as x. But suppose that not only x, but we have some companion operators, x hat. And suppose that they satisfy this relation, where H is a local Markov matrix that I've shown you in the beginning of my talk. And I omit all the indices here, relying on your intuition. Anyway, so if this relation is satisfied, then the periodic stationary states under the periodic boundary condition is expressed in this manner. Why? So if you apply the Markov matrix, then it's a sum of little h in many places, the first copy and second copy and so on. And I applied already this hat relation or cancellation mechanism. But you see that this is systematically cancelled out due to the periodicity or cyclicity of the trace. So somehow the construction of the stationary probability is reduced the problem of finding the operator, not only operator X, but a companion operator X hat satisfying this relation. But this problem can further be kind of elevated to the Zamolodchikov-Faddeev algebra. So here S structure function is a so-called stochastic L matrix at Q equals 0. I haven't detailed this in my talk, I'm sorry, but this is easily found from the definition of our ASEP dynamic, ASEP dynamics. So it's a function of Q and this spectral parameter. And here, what is essential is you need an operator X depending on the spectral parameter X. So you need to invent certain operator X spectral parameter dependent version of this matrix product operator. Then you take the derivative and with appropriate initial condition, you recover this. So the construction of the stationary state or stationary probability is reduced to the problem of finding the representation of this ZF algebra, of which this S is known in our problem. Well, legally speaking, we need to assure that this trace is non-zero finite, but this can be assured. So can we find such spectral parameter dependent version of that Fourier transform matrix? And what we found is this. So the spectral parameter is given by this. So you remember that this is a statistical sum for all the edges except this southeast diagonal. So it's a huge sum, but every time you decide these summation variables or configurations, you have some alpha 1 to alpha n. These are 0 or 1. Depending on the choice, we introduce extra factor here. Now, our task is to prove the ZF algebra, which takes this form in our problem. So this is effectively gives this information of this guy. So our task is to show this equality for this object, which is very highly non-local and non-trivial. This is very non-local. So we take the following strategy. First, we generalize the problem to bringing Q back by bringing Q back. So that's Q melting. And this CTM becomes a layer transfer matrix. And these relations are kind of elevated, generalized to their bilinear relations. Still, it's non-local. But it turns out that it can be reduced to the single local relation, which turned out to be nothing but a tetrahedron equation. Somehow we generalize the problem further and further until the point that it can be most transparently shown from the generic perspective. And that endpoint, a terminal, turned out to be the tetrahedron equation. So let me explain these steps in the remaining minutes. So the first one is a Q melting. So because I introduced Q back, so the last vertex is coming back. So it becomes a 6 vertex model, but I introduce extra spectral parameter here. So again, this curly L is an operator acting on the Fock space, indexed by these 4 indices and takes the forms of 6 vertex model. And now using this as a building block, I construct a layer transfer matrix by this diagram. So this is a square lattice. I mean, this black arrows forms a square lattice. And I specify the boundary condition at the right and bottom. So that's the south and east are fixed. But otherwise, it's free. So the northwest free and southeast fixed boundary condition layer transfer matrix. Layer from this layer to this layer, following these blue arrows. So I think this is clear for everyone. So it's an operator acting on the distance product of the Fock spaces. This is n by n lattice. And remember that the A, J are not the indices of a matrix, but it's a level of the boundary condition. Now, it turns out that this layer transfer matrix satisfies a bunch of relations, and I picked up a few, 1 and 2. For example, for fixed AJ, it forms a commuting family. But you can also mix A and J in some sense. Such relation holds. The fact that DF relations are included in these two cases, if you specialize Q to 0. So when you specialize Q to 0, so this southeast triangle part is frozen effectively, and you are left with a corner transfer matrix triangle shape. That happens when Q equals 0. And what's the origin of this 1 and 2? So they are the special case of the most general bilinear relation of the layer transfer matrix. So I'm not going to explain the detailed condition, but it's basically something like this. So you take the product of X and Y with various boundary conditions A, J, and A prime and J prime with a bit of the prefactor depending on X and Y. And the result is symmetric with respect to X and Y. So you don't have to care about this precise description, but there is such general bilinear relation for layer transfer matrix. So our task is to prove this relation. And we are coming to the final ingredient of the talk. So for the proof, we need to introduce one more 3D L operator, which is obtained by L by replacing Q by minus Q, and I denote it by M. And reflecting this replacement, I change the color from blue arrow to green arrow. So these black arrows at 0 are 1, and blue arrow and green arrows are Fock space. And now it turned out that they satisfy the tetrahedron equation, which looks like this. So it's the equality of linear operators on this space. So you see the indices run from 1 to 6. So 1, 2, 3, 4, 5, 6. So 1 to 4 are the C2, which correspond to the black arrows. And fifth component corresponds to the Fock space represented by blue arrow here. And the last component is again the Fock space represented by green arrow here. And for example, this factor 245L is here. Then you have to apply 135 here. And the next one is 346 here. And the last one is 126 here. Right? So these arrows faithfully represent the order of the product of these operators. And the right-hand side is obtained by reversing the tetrahedron. So in the Yang-Baxter equation, you reverse the triangle. But for tetrahedron equation, the elementary simplex in the 3-dimensional, you reverse the tetrahedron. And that was originally proposed by Sasha Zamolodchikov in 1980. So this particular form of the tetrahedron equation holds. The proof is not so big deal. But how to use this local relation to show this bilinear relation? This is just one page. So if you consider the Tx, product of Tx and Ty, then that means you have to place the layer attached to the spectral parameter X in front. And then back plane is you have to assign the layer associated to a spectral parameter Y. The front layer X, back layer Y. And here it's reverse. So that's the product of Tx and Ty. But I introduce the extra wire or arrows, green arrows here, and make some of the arrows cross in this manner. And what's the use of this? Look at this piece of the diagram. So it exactly fits this diagram, and you see that in the role of the tetrahedron equations, you exchange the order of x and y from left-hand side to right-hand side. So x and y gets reversed if you push green arrow through. Oops. So starting from this place, you push the green arrow and thereby reversing the order of x of front layer and back layers. You can push and push and push it through until you totally reverse the order of the two layers associated with x and y. So the left-hand side more or less corresponds to tx, ty, or maybe, tx, ty, and this is ty, tx. And the last step is to remove the artificially introduced green arrow. And that can be easily done by evaluating both sides between various left and right eigenvectors m, running along the green arrow. And that's the end of the proof. So I have to emphasize that this line of argument is done without relying on Ferrari-Martin algorithm. We just constructed corner transfer matrix, like three-dimensional layer transfer matrix, and we were able to prove that the homological algebra relation using a single local relation, which is tetrahedron equation. So that means we have connected everything. So Ferrari-Martin algorithm is one aspect of this construction, and the commutativity of the layer transfer matrix is controlled by tetrahedron equation. So the matrix product formula and Ferrari-Martin algorithm is kind of connected, interrelated through this construction. So that's an independent proof without relying on the FM algorithm of the matrix product formula of the stationary probability. So that's almost the end of the talk. So, but a quite parallel story holds also for a class of n species totally asymmetric zero range process where particles obey some priority rule to hop to the neighboring sites. So the rough image is like this. Actually, this N-TASOP and N-TASEP I've talked about, they are the sister models. So from the point of Yang-Baksa equation, our R matrix is associated with anti-symmetric tensor representation, and we are concerned with the 3DL operator and for the TASEP. But the parallel story is holds for the R matrix for the symmetric tensor representation. And associated, there is an associated solution to the tetrahedron equation, which is referred as a 3D R operator, and that's L-TASOP. So maybe in the paper by Ayyer and Travis, it's called fermionic and bosonic. Anyway, these are the models without containing parameter. But the natural Q version of these models can be formulated using the stochastic R matrix, and some results has been also obtained. So this is a final remark. We have talked about these things. So this is a one-dimensional model, and we introduced three-dimensional operators and did some procedure. Especially, we identified the so-called multi-line Q's construction as a corner transfer matrix. That was a key idea, and obtained this operator. But that was a sort of prologue, as I mentioned in the beginning. So actually, so many years, I wondered if it may be possible to extend it to that ASEP in a naive way, but I couldn't. But very recent work by James Martin and Cortell and Ramanujan and Williams, they somehow succeeded in obtaining the stationary probability for these models using multi-line Q construction. So then, I'm interested if it may be possible to reformulate their result in terms of corner transfer matrix and do the similar story. So we have partially done it, and it was successful, but there was a price to pay. So we had to introduce a very strange T-boson 5 vertex model rather than the usual one. So I already had the T-boson 6-particle model, but it was not usable in that form here. So I had to resort to some very strange T-boson 5-vertex model. That was the reason of the title. But anyway, it was done to some extent. But at the moment, I don't know any hidden 3D structure here. So if you are interested, please look at this paper. So that's the end of my story. Thank you.
Are there any questions?
So, yeah, thank you for a nice talk. So, can you use this things that you built up at a higher level to compute some things out of equilibrium, like in the TASEP, like in the multi-species TASEP, like the diffusion constant or something?
We haven't done it for the TASEP, but for zero-range process, two-species zero-range process, yes, I have done some work about the currents with Magazev. Yeah. Yeah.
But the current is still the stationary current, right?
Yeah, stationary current.
But can you do something like out of equilibrium?
Sorry, we haven't tried.
Okay, thanks. Sorry? No.
So can you explain the arrow that says T goes to 0 in the bottom where it's crossed out?
Yeah.
Can you explain that?
Okay. Yeah. So we have recovered matrix product operators, which was known by Cantini, Dogia, Wheeler, Melbourne people. I don't know about Cantini, but anyway, so this was known matrix product operator, but there's no known graphical representation that fits a corner transfer matrix picture. So we did that. So now it can be interpreted as a corner transfer matrix of certain strange 5-vertex model. But if we naively set T equals 0, it doesn't go to this operator that I explained in this talk. So that means these matrix product operators are not necessarily unique. Especially when T equals 0 situation, there should be some loop that you can check other choices. So that's the status. But nevertheless, of course, this gives a stationary probability. Yeah, of course.
So is there hope of finding a different operator that does specialize correctly?
Pardon, so I couldn't catch.
Is there hope of finding a different operator that specializes correctly at T equals 0?
I think this is a good object. Well, not so sure, but so maybe there may be some other operator here. Yeah.
Thank you.
Questions? If not, let us thank Kuniba-san again.
Thank you.
We resume at 5 minutes to noon.